using diverse parents to have a chance to create different offsprings with different characteristics. This part of first parent, this part of first parent, and this part of second parent, and mix them to have this child. Something happens, and if it's more than that, there would be no mutation. Hi everybody, welcome back to another video in Artificial Intelligence course in Farzin Academy YouTube channel. Today we want to start very important concept, evolutionary algorithms and genetic algorithms. In this chapter, we want to use the process of evolution and Darwin's theory to model our problems and solve them using these algorithms. So in this video, actually I want to divide this chapter into two videos. So this is the first video and I gonna share and upload the second part after this. So in this video, we will see main ideas, some techniques, and have a few examples. And in the next video, we will complete this chapter. So let's start it. As I told you, we use the process of evolution, Darwin's theory, to model our problems and solve them using evolutionary algorithms and genetic algorithms. Well, we say a population of individuals. When we say individual, we are modeling our states, our nodes in our space state or our graph into a population of individuals. So a population is the set of all states and all nodes, and each individual would be one state or one node. So a population of individuals creates a new generation by producing offspring. So what is offspring or kid or child? That would be a successor state. So this is the terms that we map from a graph into a population because we're talking about evolutionary algorithms. So we have to use its special terms. So here is two important terms that we should know. First one is fitness, that we say it's a measure for evaluating quality. It's like objective function, and we try to maximize this measure. And second one is evolution. That would be the improvement of the next generation's fitness. That means right now we have a generation, a population of individuals, and consider the fitness of our current population is a number like X. The evolution is the improvement of next generation fitness. That means we want to make this X bigger and make it better. That is the process of evolution, improvement of next generation's fitness. And here are two important terms. First one is convergence, that we say producing a generation with similar characteristics and high quality, and divergence is producing a generation with greater diversity and higher quantity. So there is a trade-off between convergence and divergence. Both of them have pros and cons, and you have to probe your current generation and use one of these to make your fitness better. When we use convergence, we have similar characteristics. So if the parents in our population that they want to procreate an offspring, they have good characteristics, we use convergence to have similar individuals as their offsprings, and it helps us to have high quality. But when our current generation characteristics are not good enough, we try to have offsprings using diverse parents to have a chance to create different offsprings with different characteristics with this purpose to improve our fitness. So when you want high quality, you use convergence, and when you're looking for greater diversity and higher quantity, you use divergence. And finally, what is an evolutionary algorithm? We say it's a population-based local search algorithm. So the area of evolutionary algorithms and genetic algorithms in local search algorithms. Do you remember our previous videos about local search or non-classic searches? Algorithms like hill climbing, simulated annealing, local beam search, and so forth. If you like to watch those videos, I've provided the link of the AI course playlist in the description of this current video. So all you have to do is click on the link and all videos will be shown for you, and you can pick each video that you want and watch it. So let's continue our video. We say challenge of evolutionary algorithms is premature convergence. It means at a point you converge into some characteristics that you stuck in that point and you wouldn't have any diversity. And this is not a good thing. And what is the drawbacks? We say lack of improvement from one generation to the next. If you stuck in one generation characteristics or premature convergence, there would be no chance to make your fitness better, and you wouldn't be able to improve your generation after each one. So it caused getting stuck in a local optimum. We will see that we've seen that in algorithms like hill climbing and simulated annealing, and inability to escape from it. So these are drawbacks of premature convergence. And there are some techniques that we will use in evolutionary algorithms and genetic algorithms that they are very useful. Let's see them. First one is representation. This is the way that we encode our problem states into a linear form or array-based form. Well, so far when we want to take care of our artificial intelligence problem, we use a graph with some states, edges, and some measures. But here in evolutionary algorithms, we encode our states of graph into an array or a linear form. As you can see here, we could have real numbers and integers or even binary numbers. So consider each array as an individual in your population, or each array is one state or one node of your graph. And you would have some approaches to apply on your arrays. One of them is crossover. It means applying operations on two parents and generating offspring with a random combination of parents' traits. So crossover helps us to have a new individual using two parents. So consider these two arrays, blue one and yellow one. Consider these two arrays as two individuals, and they would be parents and they want to procreate an offspring. So we can apply crossover to have an offspring using these two parents. So there are multiple ways to apply crossover. The first one and the simplest one is one-point crossover. That is selecting a single point for transferring the parent's genes. So as you can see here from these two arrays, I set this point to apply my crossover. So I have this line here and I can combine the genes of these two parents, the characteristics of these two parents to procreate new offsprings. So I would have two offsprings or two children, as you can see here. I have the left part of first parent and the right part of second parent, mix them and have one child. And for the next child, I mix the right part of blue parent and left part of yellow parent to have second child. So this is the way that we can use one point or single point crossover to have children from our individuals or our parents. And we can do the same thing for binary numbers. I have this point and mix left part of first parent and right part of second parent for having this child, and right part of first parent and left part of second parent to have second child. So a single point crossover or one point crossover, we can apply it even to binary numbers. And we can have multi-point crossover. That means we do not just have one point, we can have several points. In this example, I'm using 2 points and mix these two parents to have two different children. And as you can see, for example, for first child, I have this part of first parent, this part of first parent, and this part of second parent, and mix them to have this child. So this is the way that we apply crossover to have new offsprings and new individuals in our population. And also we can do the same thing in binary numbers. This is so obvious. And another method that we can apply crossover in to our parents is averaging crossover. That means we generate an offspring with a random weight between 0 and 1 that is suitable for real valued numbers. So consider I have two parents, P1 and P2. You can see the arrays. For P1 I have 5, 3, 8, and for P2 I have 2, 4, 6. And I want to play averaging crossover. So I would generate a random number between 0 and 1. So consider we call it alpha, and it's equal to 0.3. And I have to calculate 1 minus alpha, and that would be 1 minus 0.3, that would be 0.7. And I multiply this value into all numbers of P1. So we would have 1.5, 0.9, and 2.4. And also we multiply 1 minus alpha, or 0.7, to all numbers of second parent. So we would have 1.4, 2.8, and 4.2. So I have alpha P1 and 1 minus alpha P2. And I perform addition into these elements of arrays, and I would have one final child that I show it like this, and we represent it as C for our child. And this is the result of addition of these values into each other. The first element with first element, second element with second element, and third element with third element. So this is the way of averaging crossover to have offsprings from two parents using crossover. The next concept that would be too important too is mutation. We call it random error of nature. That means we set characteristics of our offspring not just because of the features of parents, because of some error of nature, some characteristics changed, and we would have different generation for our offsprings. So we control this mutation by a probability parameter that we call it PM, probability of mutation, and it's sometimes a low value because the probability of mutation in real world is very low too. So there are some different ways to have mutation. The first one is random swap. For real numbers, we say two values are exchanged. So consider we have this individual and consider these two values that I show them with vibrant blue, 2 and 7. And we can easily swap these two things, and this is the first form of mutation. Or we can for binary numbers, we can have bit inversion. For example, I have two values, 1 and 0. I can just flip this bit, so I make 1 to 0 and 0 to 1. This is another way of mutation. And we can have one value and change it into a random value. So consider I have 7 and change it into a random value, not just swapping with another value. We change it with some random value. And the last way of performing mutation is adding Gaussian noise to our elements. So consider I pick this value 7 and I generate a random value between 0 and 1 that we call it Gaussian noise. So consider it would be 0.2. So I add 0.2 to 7 and my new value would be 7.2. So you see different ways of performing mutation and how we consider to perform mutation on our individual. Well, we set PM to a low value like uh, this 5% of happening, and then we generate a random number between 0 and 1, and when this random number is less than this probability, the mutation happens, and if it's more than that, there would be no mutation. So this is the end of this video. Our chapter is still going on. I will upload the next video. We will have some new concepts of evolutionary algorithms and genetic algorithms. We will complete this chapter and see different examples, and we will learn how to model our AI problem using evolutionary algorithms and genetic algorithms. So if you enjoyed this video, that would be a big help for me and my channel to subscribe my channel, like this video, leave a comment, and share this video with your friends who are interested in artificial intelligence and computer science. Thank you very much. See you later.